Imagine taking a solid block of metal and turning it into a perfectly shaped machine part with incredible precision, a hole exactly where it needs to be, a curve with almost no visible error, a surface smooth enough to look polished, and all of this without a human controlling every single movement. Instead, a computer tells a machine exactly where to move. This is CNC machining. CNC stands for Computer Numerical Control. And it has completely changed the way engineers manufacture precision metal parts. But how does a computer turn a digital design into a real object? How can a machine cut steel, aluminum, titanium, and other tough materials with such incredible accuracy? And how does it know exactly how much metal to remove? To understand that, let's start with the simplest possible thing, a block of metal. At the beginning of the manufacturing process, the material may look nothing like the final component. It could be a rectangular block of aluminum, a heavy piece of steel, or specially prepared piece of titanium. The finished part might contain holes, channels, curves, pockets, and complicated surfaces, so the machine has to remove materials step by step. But before the machine ever starts cutting, the part exists inside a computer. Engineers create a three-dimensional digital model. Every important dimension can be defined: the length, the width, the height, the diameter of a hole, the depth of a pocket, and even the shape of complicated curves. This digital model becomes the foundation of the manufacturing process. But a CNC machine cannot simply look at the model and understand what to do. The design has to be converted into instructions. Those instructions tell the machine where the cutting tool should move, how quickly it should move, how deep it should cut, and which tool should be used. This is where computer-controlled machining becomes extremely powerful. Instead of manually turning wheels and controlling every movement, the machine follows a programmed sequence. The cutting tool can move along different axes. It can travel forward and backward, side to side, up and down, and in more advanced machines, several movements can happen at the same time. This allows the cutting tool to follow extremely complicated paths. But there is a major challenge. The material is strong. A cutting tool has to physically remove that material. That creates force, it creates heat, and it can create vibration. If the machine moves too aggressively, the cutting tool can become damaged. If the cutting speed is wrong, the metal can overheat. And if the machine vibrates too much, the final part may have an imperfect surface. So CNC machining is really a carefully controlled battle between a cutting tool and a piece of metal. The cutting tool is usually made from extremely hard materials. Depending on the application, manufacturers can use carbide tools and other specialized cutting materials. These tools have cutting edges designed to remove tiny pieces of material. As the tool moves through the workpiece, small chips of metal are produced. Those chips may look insignificant, but millions of them can represent the material that has been removed to create the final component. And the machine has to control this process extremely carefully. One of the most important factors is cutting speed. The tool may rotate at thousands of revolutions per minute, but faster isn't always better. If the tool rotates too quickly, heat can build up, the cutting edge can wear faster, and the material can behave differently. If the tool moves too slowly, production becomes inefficient, so engineers have to find the right balance: cutting speed, feed rate, depth of cut, tool geometry, material type. All of these factors matter, and that's why CNC machining is much more complicated than simply putting a metal block into a machine. The machine also needs to know exactly where that block is located. Before cutting begins, the workpiece is securely fixed to the machine. Special clamps, fixtures, or holding systems prevent it from moving, because even a tiny movement can cause a major problem. Imagine drilling a hole that needs to be perfectly centered. If the workpiece shifts slightly, the hole may end up in the wrong position. For a simple object, that might be inconvenient. For an aircraft component, engine part, medical device, or precision machine, it could make the entire component unusable. This is why CNC machines are built around stability. The machine structure needs to be rigid. The motors need to be precise. The guide systems need to move smoothly. and the cutting tool needs to remain stable while removing material. But there is another important system inside the machine: sensors. Modern CNC machines can use sensors and measurement systems to monitor what is happening during manufacturing. Position sensors can tell the machine where its moving components are. Other systems can help detect tool wear, temperature, vibration, or unexpected conditions. This creates a feedback system. The machine doesn't simply move blindly. It can constantly work with information about its position and condition. Some advanced manufacturing systems can even measure the finished part. A precision probe can touch specific points on the component. The machine compares the measured position with the required dimensions. If something is slightly outside the acceptable range, engineers can investigate the process. This is extremely important when manufacturing thousands of identical parts, because CNC machining isn't only about making one perfect component. It's about making the same component again and again, with consistent dimensions. Now imagine a factory producing engine components. One part comes off the machine, then another, then another. If the process is properly controlled, each component can be nearly identical. That's one of the biggest advantages of CNC manufacturing: consistency. A human machinist can be extremely skilled, but manually repeating the exact same movement thousands of times is difficult. Computer-controlled machine can repeat programmed movements with remarkable consistency, and this is where automation becomes even more powerful. Modern CNC machines can automatically change cutting tools. Imagine one tool drilling a hole, another tool creating a pocket, another cutting an outside contour, and another performing a finishing operation. Instead of an operator manually replacing every tool, the machine can use an automated tool changer. The machine finishes one operation, moves the current tool away, selects another tool, and continues the manufacturing process. This can dramatically reduce production time, but CNC machines are not limited to simple shapes. Some advanced machines can create extremely complicated components. They can cut curved surfaces, angled channels, precision pockets, and complex three-dimensional shapes. Multi-axis CNC machines can move the cutting tool around the workpiece from different directions. This can reduce the number of times the component needs to be repositioned, and that can improve accuracy. The fewer times the workpiece is removed and reinstalled, the fewer opportunities there are for alignment errors. This is especially important in industries where precision matters enormously: aerospace, automotive manufacturing, medical equipment, robotics, energy systems, and high-performance machinery. In these industries, a tiny manufacturing error can sometimes have serious consequences. That's why CNC manufacturing often includes several stages. First, the raw material is prepared, then the workpiece is secured, the machine establishes its position. The first cutting operation begins. Large amounts of material may be removed quickly. This is called roughing. The goal is to get close to the final shape. After that, the machine can perform finishing operations. The cutting becomes lighter, the tool follows more precise paths, and the final surfaces become smoother at the end. The finished part may be inspected, its dimensions can be checked, its surfaces can be examined, and its critical features can be measured. Only after the component meets the required specifications can it move to the next stage. But what happens to all those metal chips inside a CNC machine? The cutting process can produce a surprising amount of waste material. That's why many machines use coolant. Coolant can help control temperature, reduce friction, and carry metal chips away from the cutting area. The chips fall into collection systems in many factories. The metal can later be separated and recycled. So even the material removed during manufacturing doesn't necessarily have to be wasted. Now here's something fascinating. The precision of CNC machining doesn't come from one magical component. It comes from the entire system working together. The computer software, the motors, the mechanical structure, the cutting tools, the sensors, the work-holding system, and the operator or engineer all have to work correctly. If one part of the system is poorly designed, the final result can suffer. That's why CNC machining is really a combination of several engineering disciplines. Mechanical engineering controls the machine structure and movement. Electrical engineering controls motors and electronics. Computer systems control the instructions. Materials engineering helps determine how different metals should be machined, and manufacturing engineers bring all of these systems together. The result is something remarkable. A computer-designed object becomes a real physical component, one tiny cut at a time, and the process can be repeated thousands of times. But CNC machining is still evolving. Modern factories are becoming more connected. Machines can communicate with production systems. Sensors can collect huge amounts of data. Software can monitor machine performance, and automation can coordinate entire manufacturing lines. This means the future of CNC machining isn't simply about making machines move faster. It's about making them smarter, more precise, more efficient, and more capable of detecting problems before they become expensive failures. Some factories are moving toward highly automated production cells where CNC machines, robotic arms, inspection systems, and material handling robots work together. A robot can load a metal blank into the machine. The CNC system can perform several machining operations. Another robot can remove the finished component. A measurement system can inspect it, and the production system can record the results. The entire process can happen with very little manual intervention. And that brings us back to the original question: how can a CNC machine cut metal with such incredible precision? The answer isn't simply because it's controlled by a computer. The real answer is much deeper. Precision comes from controlling every part of the manufacturing process. The computer controls the instructions, motors control movement, sensors provide information, rigid machine structures prevent unwanted movement, cutting tools remove material in carefully calculated amounts. Coolant manages heat, and inspection systems verify the final result together. These systems transform a rough piece of metal into something that may eventually become part of an aircraft, a car, a medical machine, a robot, or another precision-engineered system. The next time you see a perfectly machined metal component, remember that its smooth surface and precise shape didn't appear by accident. Behind that component is a chain of engineering decisions, digital design, computer control, mechanical movement, cutting technology, measurement, and precision manufacturing. A CNC machine may look like a giant metal box from the outside, but inside, it's a highly coordinated system of computers, motors, sensors, tools, and physics. And every tiny movement matters, because when a machine is removing metal, even a fraction of a millimeter can make the difference between a perfect component and a useless one. That's the real power of CNC machining. It doesn't simply cut metal, it turns digital engineering into physical reality, one incredibly precise movement at a time. If you enjoyed this engineering documentary, subscribe for more fascinating stories about machines, technology, automation, and the engineering systems that quietly build the modern world. I'll see you in the next documentary.